Welcome to my channel. In this video, we are going to be showing how to calculate the magnetic field at point P along the axis of a circular loop carrying current I. The point that we're interested in, P, to this point is given as H. Then we have the y-axis, the x-axis. Then we have the radius from the center to this point where this part is the elemental change of the wire. Okay, so the magnetic field as a result of this entire circular loop is given by this formula, and this formula is known as the Biot-Savart law. Once we know this value and we know this value, then everything is easy for us to solve. So to get these values, we move on to the next slide. Now, if you recall that we have the expression for dl is given as dx x cap plus dy y cap. Okay, but we know that our x is equal to a cos theta, our y is equal to what? A sin theta. Then because we have the x here, then we need to change this one with respect to theta. So the change of x with respect to theta is given by this expression. Likewise, because of this dy, we have dy, we need to change this one with respect to theta, and it gives us this. So if we substitute this and this into this expression, we have dl equal to this expression. Now that we have this expression, then we move to the next expression, which is this vector position. To get this vector position, it is given as minus x cap a cos theta minus y cap a sin theta plus z cap h. Mind you, this expression, especially for the x part, is not coming from this part, and this y part is not coming from this part. For you to get this, we need to visit the diagram again and see how it can be determined. From the diagram, we can see that we have a path from this point to this point, which is this r minus r prime. But we can follow another path which is different from this, and that path is moving through this path and what? Upward. Well, if you notice that this path can be written in terms of my y and my x, and once this path is written in terms of my x and my y, then for us to move to this point, from this point to this point, I must reverse this position backward. That's why it's taking negative sign. And this particular y, I must reverse it backward. That's why this y is also taking negative sign. Then it goes up, it becomes positive. So that's why we have the negative x cap a cos theta, negative y cap a sin theta plus the z cap h. Once this one is known, then this one is clear. All we need to do for this is to take the magnitude of this, which is a squared cos squared theta plus a squared sin squared theta plus h squared. All because of these 3 raised to power 3, we have raised to power 3, but the vector is divided by 2. Because of the magnitude, we have to divide by 2, which means the cube and divided by the cube and the square root of this expression. Now from this, we can simplify this expression by factorizing a squared out. Then we'll be left with cos squared theta plus sin squared theta, and that will give us 1. So at the end, we are left with a squared plus h squared, 3 over 2. Now that we have this expression and this expression as this, we can now substitute back to the Biot-Savart law, which is given as h. From this point, we now see that this is my dl with d theta, and this is my vector position in terms of my x, y, and z axis, divided by 4 pi a squared h. From here, recall that this symbol, this expression here, is a cross product. So we have to take the cross product of this expression and this expression. To take the cross product, we'll take this one cross this, this cross this, this cross this. And one of the law of cross product is that x cross x is equal to 0, and y cross y is equal to 0. Then z, okay, x cross y will give us z. So that's same pattern. So when you cross this one and this one, you get this expression. You can try it yourself. You will get exactly this expression. So once you have that, I think we should take note that this one is, these are vector positions. So once you have this expression, then we move to the next stage, which is multiplying this IA throughout. So once we multiply our IA throughout, we'll get this expression with respect to theta. Then what you notice is that there is IA, there is IA, and there is IA. And this one all together, we'll factorize them out and get this expression, leaving integral of cos theta plus integral of sin theta h, then plus integral of this particular expression. If we integrate this one with respect to theta from 0 to 2 pi, it goes to 0. If we integrate sin theta with respect to theta from 0 to 2 pi, it goes to 0. So that's why the first two terms are equal to 0. But this particular one, if we integrate this particular one, it gives us a theta from 2 to 0. From 0 to 2 pi, sorry. Now the next thing is that we have this expression as theta. If we substitute these two values, the upper and lower limits, we'll get this expression in the z-axis. So from here, this one reduces to this by 2 pi cancelling 4 pi, leaving this particular expression. So this is a magnetic field given as this expression, which is the general known formula for magnetic field along the axis of a circular loop. Or we can write it in terms of the magnetic induction, which is mu naught h equal to mu naught I. So we'll just add mu naught in the z-axis. So this is the formula. But sometimes you might be interested in calculating the magnetic field at the center of the circular loop. So what you do is to make h equal to 0. Once you make h equal to 0, this formula will become this expression. And at the end, we have our B, which is magnetic induction, is equal to mu naught I a squared all over 2a cubed. So if we cancel out, we have B equal to this. So this is a magnetic induction at the center of the circular loop. I hope this helps. Thank you for watching.